This video will show you how to set up a simulation of a density instability using the level set method in Comsol. We start by setting up a model. Let's do a 2D model, and we need to put in some fluid flow physics where we'll use multi-phase flow, and we will select two-phase flow, level set, laminar flow. That'll do it. And then we'll use the time-dependent with phase initialization study. There you go. See, there's two steps in that study. Now we'll put in the geometry. This will just be a square that's 10 meters by 10 meters. We put it in as a rectangle. And we'll add a line segment, a horizontal line segment at half height. And it has those coordinates, and I'll show you what that looks like here. There's the line at half height, and you can see there's the rectangular square, and then there's the line. And that will divide the two different fluids that we'll use. So the physics has a laminar flow and a level set component. The laminar flow is here, and we're just using the defaults. We need to put in gravity though, so we check gravity up at the head node there for the laminar flow physics, and we need to put in a pressure point constraint. That's under points, boundary conditions there, and we put in that pressure is equal to 0 in the upper right hand corner. The model will probably won't run if you don't do that. So level set, this is just the default here. And then the initial values, we have two fluids, and we need to decide which one is going to be fluid 1 and which one will be fluid 2. So I set them up like I showed you there. You can put in the different initial values there. So you'll need to put in a second fluid for the initial values. And then we got to go to the multiphysics to set that up. We have two-phase flow, and this is where you're going to set up the different fluid properties. So fluid 1, which we defined up in the level set, has proper density of 1,000 and viscosity of 10 to the minus 3 Pascal seconds. There's the properties of water, and you can see that that's where fluid 1 is. Fluid 2 is there. It's the upper fluid. And so that's going to be the more dense fluid, and it's going to have a density there of 1,010. So just a 1% larger density, and the viscosity is going to be the same. We can experiment with those properties later. There will be surface tension between those, and I just use surface tension between air and water. And there's a contact angle of pi over 2. That's in the wetted wall. All the walls we'll assume are wetted. And then we'll go ahead and run this. And I set it up for 65 seconds. And we can display what happens as the simulation goes. You can see this is the deformation that occurs as a result of the density. The white fluid on top is more dense than the black fluid underneath it, and the interface deforms like that. This is what the velocity distribution looks like at the end of the simulation. And yeah, there's the default pressure. This is the volume fraction of the fluid. This is the default plot, and I changed the format around a little bit. This is just what you get from the default. There's the volume fraction for phase 1, and I changed the format a little bit here to give this black and white image. I did that by restricting the data range from 0.45 or 0.5 to 1. And then if you go down below, I don't show it there, but the color and style I set to black instead of the color flood. So that's why you get just the one color. And then also I made an animation of this because I wanted to explore what happens with the dynamics. So I used the player and set it up to do an animation of a black and white image. So you set that up, and then you can run the image, run the simulation as an animation with that slider, and that allows you to go through and see how that density and stability progresses with time. Go back and forth, and you can see as the one fluid goes into the other, you get kind of a mushroom shape geometry.